In the previous video, we covered the basics of sequential circuits and SR flip-flop. In this video, we are going to discuss about the D flip-flop. So the D stands for data input, and it has one input and two output, Q and Q bar. Now, if you check the truth table for the D flip-flop, so in the slide it is given, the inputs are given as the clock and D. These are the two inputs, and Qn plus 1 is the next stage. Now we know that when the clock is 0, whatever be the input you apply at the D in D line, the output will not change. That means without applying the trigger signal, there is no change for the output. Output will remain as the previous one. Now when the clock is 1, or when the trigger signal is applied, the output will change according to the input. If you are giving the input as 0, your output will be 0 in D flip-flop. And if you are giving the input as 1, your output of your D flip-flop is 1. So this is the truth table of D flip-flop. Next, we can just go through the logical circuit for the D flip-flop. So this is the logical diagram of your D flip-flop. Here you can see that in the blue box, this is nothing but your SR flip-flop. So your D flip-flop, it is nothing but the modification of SR flip-flop. In SR flip-flop, if you are giving S and R as the inverse of S, that is actually your D flip-flop. Here we are giving the input signal, and that signal directly come to the S terminal of your flip-flop, and the other terminal, that is R terminal, if you are connecting through a NAND gate, that means you will get a inverted output here. So here only one input D. If D is equal to 0, then S will be 0, R will be 1. So SR, when it is 0, 1, Qn plus 1 state will be 0. That means your flip-flop get reset. And similarly, when D is equal to 1, S is 1, R is equal to 0. So your flip-flop output will be 1. So your D flip-flop is the modification of SR flip-flop. Now this is a simple used for the SR D flip-flop. So to input D and clock signal, then Q and Q bar as the output. Next is the operation of your D flip-flop. So we can take initially D is equal to 0. Now when D is equal to 0, S equal to 0, here R it will be 1. Now we have to apply the clock signal in order to work your D flip-flop. So you have to ensure it is equal to 1. Now if you check the NAND gate 2, one input is 0, one input is 1. So the output will be definitely 1. 0 dot 1, its complement, it is nothing but 1. Now in the third NAND gate, that is NAND gate 3, both inputs are 1, so the output will be 0. That is 1 dot 1, its complement, it is equal to 0. Now if you check the NAND gate 4, initially the inputs are, one of the input is 1, the second input is Q bar. So the output of NAND gate 4 will be 1 dot Q bar its complement, that is nothing but Q. So the output of NAND gate 4 is Q. This Q is getting fed back as the input of NAND gate 5 and the second input is 0. So if you take NAND gate 5, one input is 0, the second input is Q. So 0 dot Q, its complement. So 0 dot Q, it is equal to 0. So 0 its complement, it is equal to 1. So this output will be 1. So this one is getting fed back as the input of your NAND gate 4. So now the NAND gate 4 inputs are 1 and 1, its complement is equal to 0. So the Q will become equal to 0 and Q bar will become equal to 1. So when you apply D is equal to 0, you will get Q is equal to 0 as the output. Now we can check what happens when you apply D is equal to 1. So when D is equal to 1, S will be equal to 1, R will be equal to 0. Again, you have to ensure you are applying the trigger signal. Now the output of NAND gate 2 will be equal to 0 and NAND gate output 3 will be equal to 1. Now this input is equal to Q bar and this input is equal to Q. Now if you take the NAND gate 4, current inputs are 0 dot Q bar its complement. That is 0 dot Q bar, it is nothing but it is equal to 0. So 0 complement, it will be always 1. That means Q is equal to 1. Now this 1 is getting fed back here. So if you take the NAND gate 5, you have both input are 1, so its complement is equal to 0. That means Q bar will become equal to 0. So here whatever be the Q bar value, you will get the output as 1. So Q will be equal to 1 and Q bar will be equal to 0 when you apply D is equal to 1. Now a timing diagram for the D flip-flop operation is shown in the slide. Here this is the input of that input signal we apply to the D terminal. This is your clock signal and this is Q. Now here you can see that initially when the first clock is coming here, when clock is becoming 1, D value is 0. So the corresponding output will be 0. Now in this region you can see that the clock is 0. So even though your input is becoming 1, your output remains as 0, that is the previous stage, because there is no clock signal. Now when the next clock signal is coming, that is here, it will check the value of D. So when the next clock is coming, the value of D is 1. So your output will go to 1. Now this clock signal enter here. Now after that here your D is becoming equal to 0, but your output will remains as 1 because there is no clock signal in this region. Now this happens continuously. That means depending upon the value of D, the output will change only when there is a clock signal. So now if you check this region, here you can see that your D is becoming 1 here, that is here, but in this region the value of clock is 0. That means there is no trigger signal, so your output will remain as 1. But as soon as your clock signal comes, that is here you can see that for this region, the value of D is 1. So your output will remain as 1 in this region, but it is becoming 0 here. So when the input D is becoming 0, your clock signal is 1. Here the clock signal is 1. So your output will change to 0. So in order to work your D flip-flop, you have to ensure that you have D input as well as the clock signal. So the output will change only when the clock signal is applied.